So, lecture number 22, particle systems, and as part of implementing the particle system, we're going to be talking a little bit about vertex arrays. So let's first talk about what we've been doing this whole course, which is ECS, right? So when I'm saying, okay, a particle system, why not just have our particles be ECS entities, right? So the main ECS philosophy that we've been feeding you so far is that everything in our game is an entity that has components and it's handled by our systems, right? Except when it really shouldn't be. And so we haven't had any exceptions so far, but today we're going to talk about that exception. So it turns out that particle systems are a case where we would rather have these objects, these particles, not necessarily be entities. And we'll see why that is. So let's explore why that is and how we can do that if they're not going to be entities with components. But first, let's talk about what a particle system is. So it may be interesting to have a system in our game which is composed of particles, hence a particle system. And a particle system is when many small, usually similar looking or similarly behaving particles come together to form a more complex system. So we have a bunch of particles. The behavior of each individual particle is typically very simple, and the lifespan of a particular particle is usually very short. But through the incorporation of many, many different particles, we may get this complex behavior emerging out of that. Now, some particle systems are used for behavior, some particle systems are used just for graphical purposes. So for example, here we have just like a very basic particle system where we have an emitter at the bottom here. An emitter, you can just think of like a location where particles are coming from. These particles spawn and they move in some direction with a certain duration and a certain color, right? So here it looks like we have some hexagons. Particles can take absolutely any shape that you want to. They don't have to be quads. They don't have to be textured. Here we have some hexagons, and this particle system emulates some sort of fire or smoke or whatever, right? There's just some place in our map we would want to have something like this where it's a little bit more dynamic than just a fixed texture or repeated animation, for example. Here we have sort of like a galaxy black hole explosion type of thing. This is another thing that you can use a particle system for. Here we have like a purple fire explosion-y type thing. If you look at it very closely, this is all done with tiny, tiny particles. So again, we get this complex behavior through using many, many simple particles. Here we have something like a dragon's breath type effect where you have some orange faded quads coming out of, this particular area over here, and it looks like a flamethrower or a dragon breath, for example. Here we have a simple smoke system that is done through a particle effect. And I mean, you could also do this through shaders as well, but this one happens to be particles. And then over here, we combine fire and we combine smoke particle systems to get something on fire with smoke coming out of it, right? We could also have a behavioral type particle system where particles follow these rules. So this is an example of a flocking behavior, for example. So you can see here sort of what particle systems are. There are many, many small particles which when together, they form some sort of overall, like bigger behavior. So you can think of particles almost like this atomic thing, and when you put atoms together, they form complex systems, right? So when you talk about particle systems, most modern game engines actually come with solutions for building particle systems. So if you open Unity, it'll probably have a particle system thing that you can just edit really briefly. So the user is going to specify the behavior and the look of the particles, and then the engine is going to handle the detail. And by varying those parameters, users can get the desired effects from their particle system. So here, for example, I'm not sure exactly which engine this is, but this is a particle engine in which you can see the user here is varying some parameters, and in real time, they're seeing this thing update, okay? So this is like some sort of snowflake type thing. Here we have like this ring of fire, and the user is varying some of the parameters in the user interface here to get exactly the type of effect that they would want. But of course, this is in an engine, right? That's like a big complex engine, and we are not going to be using some complex engine. In this course, we are actually implementing things for ourselves. So in this lecture, what we're going to be doing is implementing our own, albeit basic, but functional particle system from scratch. So then why don't we want to use ECS for particles? Why couldn't each particle just be an entity and we'd have our current game system work, right? So it's possible. It's completely possible to do that, but it's really inefficient. Why is it inefficient? We may want hundreds of thousands of particles being created and destroyed every second, maybe even every frame in our game. And these thousands and thousands of particles, well, even if we're using a memory pool, particles usually aren't using any of these components that we've been doing, right? Like, particles don't necessarily have an animation. They don't have an input component. They don't have all of these components that other entities may have. Particles' behavior are very, very simple, right? So each particle basically is just going to store some minimal amount of data, like what shape it is, and where it's moving, essentially. And then the particle system will update it based on that. So we don't want, especially if we're not using a memory pool for our ECS system, the heap allocations of tens or hundreds of thousands of particles will slow down our system to a crawl, right? So we want a system that's not dynamically allocating memory, and we want this data to be very contiguous. And even though our ECS system accomplishes some of those things, if we use memory pooling, we're still wasting far too much memory on all of these components that particles wouldn't be using. So here is sort of the overall architecture of a common type of particle system that you'd have. First is that you'd have some sort of memory field. This is the way that Valve describes their particle system. And a memory field is going to be a contiguous block of memory that's allocated for particle storage, right? And we talked before, if you go back to one of the previous lectures on the memory pooling, contiguous memory is amazing for cache coherency. It's going to have a renderer, right? So we're going to have to define somehow how the particles are actually drawn to the screen. We're going to need an initializer. That's how you actually define the initial particle data, so maybe where it is, where it's heading, that sort of thing. You may need an emitter. So if your particles are going to be appearing to be coming from a particular place on the map, then you might want an emitter that actually, spawns these particles. And you're going to have some forces as well. So define the physics of the particles and say, okay, are the particles moving? Are they exploding? Do they change color? Are they bumping into things? Are there collisions? All that sort of thing are the forces that are acting on your particles. Now, depending on your particle system, you may want other things, right? So if you're doing like flocking, for example, maybe your particles are going to have some sort of steering component. Maybe they'll need other things in here. Maybe there's like texture memory that you have to allocate somewhere. Depends on the complexity of your particle system. I'm just going to give you a basic one today, but you can see from the basic one how you could extend it to be much more complex. So here's a really nice example. I think this is actually from Roblox on their particle emitters and particle systems. But here you can see a bunch of different types of particle systems. So over here we have like a cylinder where things are falling toward the ground. Here we have a cone where particles are traveling upwards. Here is particles are sort of condensing into one space. Here we have a more static group of particles. So the point here, where the particles are emanating from or collapsing to, that might be called an emitter. So our emitter here, that's what an emitter would be. Over here, we have like a smoke-like one. So particle systems can have a number of different looks and feels. So let's go into more of the implementation details of the particle system that we're going to be creating during this class. The first thing we want to talk about is how we're going to draw our particles, because this is something we haven't discussed in the class yet, because we haven't needed to. Typically, you're only drawing a couple of hundred entities to the screen, but when you're drawing tens or hundreds of thousands of particles, you need to be drawing things faster than the way that we've been doing it. So far in this course, what we've been doing is we've been drawing every single entity with its own draw call, okay? Separate draw calls from the CPU to the GPU can be very time consuming. So in our program, we loop over all of our entities. We essentially say for each of our entities, draw that entity. And every time we go through that loop, every time we're at a new entity, the CPU has to send some data to the GPU and a command to the GPU to draw something. And that can be really slow. So ideally, we would want a way to send all of the data from the CPU to the GPU and tell the GPU to draw all the particles in just one instruction, right? So here's my analogy for this. It's like going to get groceries, right? So let's say someone in your house tells you to go get groceries. Let's say your mom is like, okay, I need these things from the store. So which is faster? So here's the first method that your mom tells you to go get groceries. She says, we need eggs. Go to the store and get eggs. So you drive to the store, you go to Sobeys, right? You get eggs, you get back in your car, you bring your mom back the eggs. Then she says, we need milk. So you drive to the store, you go into Sobeys, you get the milk, you drive home, you give her the milk. Then she's like, we need bologna. Okay, you drive to the grocery store, you get the bologna, you drive home, right? Typical Newfie shopping list. But after like the 10th item, you're saying, Mom, just give me the whole list. I'll make one trip to the store. I'll get it all, and then I'll bring it back, right? So the way we've been doing things is going one item at a time to the GPU and telling it to do that thing. But what we want to do is give the GPU the whole shopping list and then say, draw all of this for us, okay? So I hope that analogy makes sense because it's pretty close to the real thing. So the way we're going to do that is something called a vertex array. Now it sounds a little, people hear arrays and they get confused, but it's really quite simple. So vertex arrays are a way to send a single GPU instruction to draw many, many different things. There's two parts to a vertex array drawing instruction. The first part is the actual data. So we have vertex data that's stored in an array, and each vertex is going to store essentially the position and the color or texture coordinates of each of the vertices that we want to draw. The second part is the primitive type, and the primitive type is essentially going to say what type of shape do we want this vertex data to represent. So we're going to use a vertex array to draw all of the particles in one draw command. And now what I'm going to do is that there's this SFML. So SFML has a really nice system for dealing with vertex arrays, okay? Every game engine, every programming language, like if you're using DirectX, if you're using OpenGL, if you're using Vulkan, whatever, they will all have some way of implementing vertex arrays. SFML has its own way, and they're all quite similar, but they just differ a little bit in the syntax. So we're going to go over the SFML way of doing it because that's what we're doing in the course. So here, let me shut this down. I'll go back to here, and I will just open up that website link. And so here's a really great tutorial. On the SFML website, it says designing your own entities with vertex arrays. So ignore the designing your own entities part, okay? Because the entities they are talking about here are different than the entities in an ECS system. What we're going to do is just look over the syntax for creating a vertex array, which is like the first third of this tutorial. So let's look at some of the code that we have here. Hopefully this is not too small for you to read. Let me make it as big as I possibly can. So in SFML, they have the SF Vertex class. So the Vertex class, you just type SF Vertex, and it will have 3 attributes. So a vertex has a position, it has a color, and optionally, it has texture coordinates, okay? So if it doesn't have texture coordinates, then you're just drawing something based on a color. So the way we would set up a vertex is by doing this. Very, very simple. So you'd say SF vertex, vertex, so you have a new vertex. Then you can set its position to be some SF vector 2f, which we've been dealing with the whole course. So you set up the position of that vertex. Then you set the color of that vertex to whatever color you want. And then you set texture coordinates, if you are drawing this with a texture, to the coordinates of the texture that you will be drawing it with. Okay? Or instead of 3 different commands like this, you could use just the single constructor, which takes all of these, or another constructor which just takes the position and the color. So that's what a vertex is. Now let's define a primitive, right? So a primitive is something like a line or a triangle or a quad. And those primitives are going to be made up of multiple vertices. So in this example, they're making a triangle. Okay, so SF vertex array. So vertex array is the data type that we'll be using. And if you want to make a triangle, what you do is you pass in 2 things. The first one is the type of primitive that this is going to be drawing, and a number, that's the size of the vertex array that you're going to be using. Okay, so here we've called the variable triangle. This is just a variable name. It could be anything, but we've said there are going to be 3 vertices in this vertex array, and when you go to draw this vertex array, please draw triangles. Okay, so what you do is now you have an array with 3 indices in it. So you have to create vectors, you have to create vertices at each of those array indices. So they're already created for you, so you don't need to say triangle 0 equals vertex whatever. They're already created. You can if you want. But what you could do, for example, is if you just want to create or change the position, you can just say triangle 0, which is the first vertex of this triangle, dot position equals, and then a new position. So that's what they've done here. They've created they've modified the positions of these vertices to be at these coordinates, and then they've set the color of those vertices to whatever colors that they want. So there's 3 vertices, they've set the positions, and they've set the colors. Now, all you have to do is, now that you have this vertex array object, you can just tell SFML to draw the vertex array. Okay? And based on what they have here, here is what's output. The really cool thing about this is that you're coloring each of the vertices. In this example, they've colored each of the vertices a different color. And what happens is, on the GPU side of things, if you color each of the vertices a different color, it automatically sort of blends the colors together for you. So it creates a gradient. But if you had given each of these vertices the same color, then it would just draw the whole object that color. So for example, if each of the vertices was red, then it would draw this triangle red. Okay. But that's really not you wouldn't really use a vertex array to draw a single thing like this, right? We're talking about a vertex array containing possibly thousands, if not tens of thousands or hundreds of thousands of vertices. So, for example, if we wanted to draw 1,000 triangles at once, we could call our vertex array triangles and then pass in 3,000 as a number of vertices, because 1,000 triangles would have 3,000 vertices in it. And then we would set all of our things like this, and then when we passed in window.draw triangles, it would draw all 1,000 of those triangles. And so here is an explanation of how that would work for each of the different types of data points. Okay, so what this chart, or what this table here is explaining, is the different semantics. So what happens differently if you pass in a different primitive type to the vertex array constructor? Okay, so up here, right here, when we had this vertex array, this is the primitive type. So this says, when you get this vertex array, please draw triangles for me. So the first triangle will be defined by vertex 0, vertex 1, and vertex 2. The second triangle will be defined by vertex 3, 4, and 5. And the third triangle will be vertex 6, 7, and 8, and so on and so on. Okay? So this table shows you, if you specify for the vertex array this primitive type, here is the description, and here's what it will look like. So if you say SF points for your vertex array, when you go to draw it, it will be a set of unconnected points. These points have no thickness. They will always occupy a single pixel regardless of the current transform and view. So for example, if you had 6 vertices, or 5 vertices, sorry, each with these positions over here, then if you said SF vertex array with SF points 5, and you gave them these coordinates, here's what it would look like, okay? Now, if you had said lines instead of points, it will draw a set of unconnected lines. These lines have no thickness, they'll be a single pixel wide, regardless of the transform and view. So, if we had an SF vertex array of size 8, so there's 8 points, and you say, I want this to be lines, then the first line will be defined as the point 0 to point 1, or vertex 0 to vertex 1. The second line will vertex 2 to 3. The third will be 4 to 5, and the fourth will be 6 to 7. So see how that works? So if your thing here has 2 endpoints, then the first 2 vertices will be the first thing, the second 2 vertices will be the second thing, the third will be the third things. All right, so that's for different lines. Sometimes what you might want to do is actually draw a strip of lines. So if you say SF line strip, it will be a set of connected lines. So the end vertex of one line is used as the start of the vertex of another line. So if we have 5 points here, okay, so the starting point, point 1, 2, 3, and 4, then a line strip will start at point 0, vertex 0, go to vertex 1, then vertex 2, vertex 3, and vertex 4. So you're starting to see now that depending on what you tell the vertex array to actually do, or what's being represented, the output behavior will be different. Here, you can have triangles. So if we wanted a set of unconnected triangles, we could define our vertex array with these indices for the vertices. So over here, vertices 0, 1, and 2 would have these positions, and they'd all be given a blue color. 3, 4, and 5 would define the next triangle. All of them would be given a green color. 6, 7, and 8 would be dark gray, and they'd be defining that triangle. However, if we did a triangle strip, then these would be a set of connected triangles, right? So the first triangle would be 0, 1, 2. The second one would be 1, 2, 3. The third one would be 2, 3, 4. The fourth one would be 3, 4, 5. And then finally, next we could have a triangle fan. So that would be connected to a central point. So point 0 would be the central point, and then you define the radius of triangles that you want to draw. And the last one we'll look at today would be quads. So this is a series of unconnected quads. So the first 4 points would define the first quad. The second set of 4 points would be the second quad, and so on and so forth with all the different quads. Okay? So for today, what we're going to be doing is we're going to be drawing quads for our particle system. So all of our particles are going to be little tiny squares. Well, they could be rectangles, but we're going to have them be squares. So our vertex array is going to be a series of points, or a series of vertices representing quads in this format. So that's how you would specify a vertex array. And then all you have to do is say window.draw vertex array, and it will draw all of that in one go, one trip to Sobeys, not having to go back and forth to the GPU. Okay. Now it turns out that the games we've been making have been so simple that we haven't really needed this yet. Like, your games are probably still running at like 1,000 frames per second. You're only drawing a couple of hundred entities. But if you had, for example, if you were making like a top-down RPG type game, what you can do is you could make a tile map, right? So you load your big tile texture in, and then you can make a vertex array that stores, instead of colors like we've been doing up here for these quads, right? These quads are colored. Instead of using colors, we can specify texture coordinates in a texture sheet, and then we can say, hey, GPU, please draw all of these tiles at once. So it would draw all the tiles on your map in one GPU call, and it would be much, much faster. Okay? So that's how this works. You don't necessarily have to implement, for your final project, a vertex array. But if you do, your game will just be faster. And it's essentially how everyone does everything, is passing a vertex array to the GPU. All right, let's go back to the slides real quick. So that's what a vertex array is and how we will use it in SFML. So making a particle system for our game, let's do it as simple as possible. I'm going to show you the most basic possible particle system that we could have, and I'm going to create a class called particle system, and everything will be in there, okay? So this class is going to have the following. It's going to have a contiguous vector of particle data. So the particles may have like velocity, lifetime, speed, steering, whatever they need to have. We're going to have a vertex array of position and color data. We're going to have possibly some data maybe about the world or about the window. So for example, in our particle system, it's going to know how big the window is. So we don't draw anything outside the window, something like that. And also it's going to have some functions that let us do something like initialize the particles, reset the particles, update the forces for the particles, and to draw the particles. All right. So rather than put all this into a PowerPoint presentation, let's just do it live. Okay. So I'm going to just code this. I might make a few mistakes, but I think it's always more fun and easier to follow if you actually see me from the ground up implementing something like this. So let's do it. All right. So here we are in Visual Studio. I have already implemented a particle system to make sure it works. And let me just run this. And so here's a particle system that I created, I don't know, in like 15 minutes. And we can see here that we've got one little spot in the middle where all the particles are coming from. And all these particles are kind of going out in random directions with like random speeds. And then they disappear after a little while and they respawn back at the beginning. Okay, so let's see how we would implement a particle system like this. And you can see now why like this might be a lot for our ECS system to handle. In fact, let me quickly go here and in the particle system, let me just turn this up to 100,000 particles and I'll see if this runs. Yeah, so this is still running at 60 frames a second with 100,000 particles. My bitrate may have gone to crap. Maybe my face is pixelated right now, but like this can handle a lot of particles really, really quickly. So like you can see, this is still running really smoothly. If I pause it at any given time, you can see all the individual quads that are being drawn here. Okay, so let's make this. Let's rewrite this code that I wrote earlier today. So first of all, let me zoom in here. I'm going to show you the main program for this because the main program is just going to be like just getting an SFML screen, kind of like assignment 1. It's just a screen where we're drawing things. There's not a whole lot of things. So you would take this and put it into your project, for example. But just to show you, I don't have a whole ECS system here that I'm working with. I'm just doing this on a brand new project. So really simply, the first thing I do is I'm going to create a new SFML render window, and I'm going to set the frame limit on that, right? So I've got this running at 60 frames per second. Then I've got this thing called particle system old because I don't want to confuse the two classes. So I create a particle system, I call that particles, and then I say particle system.init, and I pass in the window size, for example. So you can see here when I run the program, it's in the middle. And the way that it knows to be in the middle is because the particle system has been given the window size as a parameter. Then all I do is I just like have a main loop, which just for every frame of the game, it does something. So I have, very simple user input, just says what happens when the window is closed. Then I'm going to call the update function on the particle system to update the movement or the physics of the particles. Then I'm going to clear the window to black again. Then I'm going to draw the particles to the screen, and then I'm going to call window.display. So very, very simple interface to this particle system. You construct the particle system and you initialize it somewhere initially. Then every frame you're going to call update and you're going to call draw. That's it. Really simple interface to the particle system. Kind of funny, actually. Let me show you kind of a cool effect that you could do. Let's go back to like 100 particles. I'm just going to manually edit this. And so you can see there's not many particles here. That's just 100 particles. But if I turn off the window clearing so that all the particles get drawn and stay on the screen, we can get some cool effects from that as well. And so this is essentially what happens when we don't clear the screen every time. It's kind of interesting, hey? Kind of a cool effect. Kind of screws with my eyes a little bit, though. Okay, so let's turn back on the window clearing so that we have that to work with. Okay, so over here, what I'm going to do now is I'm going to switch this back to this new particle system. And this particle system here, oops, I gotta rename that. I just have some really basic skeleton code to help me remember what to write for the lecture. So here's the new particle system, and essentially nothing is happening. Okay, so we've got a completely blank slate. This particle system is not yet doing anything, and we're going to implement what I just showed, the sort of explodey type particle system. Okay, so let's go into the particle system code and we'll see what we have in this class. So the class is really simple. I'm just including vector so I can store a bunch of particle data. And I'm including SFML graphics so that I can use SF vector 2F and stuff like that. So here's my class particle system. And inside I've got some particle data. So here I'm defining a struct called particle. And so in C++, you can do this interesting thing where only the particle system is ever going to be dealing with these individual particle data. So if I had defined this struct outside of this class, then essentially anyone in my code that included particle system would now have access to this particle struct, but I don't want anyone to have access to it. So I'm going to define this structure within this class, and that just means that only the particle system knows what a particle is. Okay, so that's just what I'm doing. So each particle is going to have, let's say, a velocity, and it's going to have a lifetime. And I don't think I need to have a speed for each particle. So let's just say we have a velocity and we have a lifetime. And so each particle is going to be moving at a certain velocity, and after a certain amount of time, it's going to disappear, and then we can define what happens when it disappears. In the particle system, so we're going to have a vector of particle data, right? I'm just going to call that particles. Then I'm going to have my vertex array, M vertices. So we just talked about what a vertex array is, and this is going to be the vertex array. And if you notice up here, my particle data didn't include a position, and it didn't include a color, right, for any of my particles. And the reason for that is because the position data and the color data is going to be inside the vertex array anyway. So I'm using as little memory as possible here because I may have hundreds of thousands of these things. So all of the positions and all of the colors of the particle are going to be stored in the vertex array. And this other data is just the stuff that's like actually defines like the physics of the particle, not the look of the particle. So the next thing I have is I'm going to store the window size. So this particular particle system might want to know how big is the window so that I could spawn it in the middle. And then I'm going to keep a variable here, which is just the size of the particles themselves. Like how big are the particles when they're drawn to the screen. Okay. Next, I have a function which is called reset particles. And when I call that, it's going to reset everything. So all the particles are going to be reset to like a randomized initial state. So inside reset particles, I have a count, a number of particles. And this is called a default parameter. So it means that if I do pass in a number, then it will use that number. So I could initialize 1,000,000 particles if I want. But if I don't specify a size, it'll just use 1024 by default, okay? And the size of the particles will be here. And let's actually, so the size of the particles is going to be defined by this. So whenever I call reset particles, it's going to reset my vector of particles to be of the size that I need. And it's also going to create the vertex array. So remember, all of my particles here are going to be quads. So it's going to be a vertex array of quads, and then the count is the number of particles that I want, and each quad has 4 vertices, so it's count times 4 vertices that are going to be in my vertex array. And we've specified SF quads here, so when I go to draw my vertex array, it will know to draw individual quads for that. Oh, let me shut this stuff down. All right, just give me 1 second here. Just turning off a bunch of notifications and stuff. All right, that should be good. So what I do then is for each of the particles, so each of the particles that I've said I'm going to have, I'm going to call this function called reset particle. And so this is sort of the overall reset everything function. And then I'm going to make this function here, which resets an individual particle. Okay, so now is where we start coding. What do we actually want to do in here for each particle? Well, maybe what we want to do is first give the particle an initial position. So we have to give it a position, right, where it's actually starting from on the in the window. Next, let's say give the particle a random angle velocity. So what that means is I sort of want let's just give it a random velocity. Okay, so we're going to give the particle a random velocity so that it's sort of, one particle with a random velocity doesn't look very interesting, but a bunch of particles, each with random velocity, sort of looks like a firework explosion. Okay, then I'm going to, so that's the initial position. Then I'm going to give the particle a velocity. Then I'm going to give the particle a color, right? And maybe I also want to give the particle a lifespan so that it doesn't just continue going on forever. It's going to reset back to its initial position at some point. That looks good so far. So let's do all of these things. So let's give the particle an initial position first. So the initial position that I want to give the particle, probably something like the center of the screen, right? So the way I give my particle a position is going to be with respect to the window size, and I'm going to use the vertex array, the vertex array m vertices to get access to those vertices. Okay, so let's give it the initial position. So I'm going to say, all right, float x equals m window size. Oops, what was that? Window size, that's my variable name. Dot x divided by 2. So this is going to be the middle x, and float my is window size dot y over 2. So I've taken my window size and I've given I've created this middle x variable to be the middle of the window, essentially. Then what I want to do is my actual particle has to be given vertices, right? So if I want to set this particle to this position, I need to go set, because I have here 4 vertices defining this particle, right? So I have to set, for this particular particle at this index, I have to find its indices within the vertex array and then set those positions accordingly. So let's go back. So what is my particle's vertices going to be in my vertex array? Well, if this particle is being referenced by this index, then the index is essentially going to be 4 times that index, right? Because each particle has 4 indices. So I will say m vertices, right? That's my vertex array. And the first vertex in that array associated with this particle is going to be 4 times index plus 0. I'm just putting in the plus 0 there to show that it's the 0th vertex. And then that's going to be SF vertex 2, vector 2f And that's going to be mx and my, right? That's the first vertex. So I'm specifying like the top left vertex of this particle. But now I have to specify the other 3 vertices for this quad as well. Because remember, I want to draw a quad for each of my particles. So let's take this, we'll copy and we'll paste it. The next vertex is going to be this one. So let's open up a little bit of a diagram here and we'll see what we're working with. Okie doke. So if I want to draw a quad, and this is going to be vertex 0, this is going to be vertex 1, this is going to be vertex 2, and this is going to be vertex 3. Now I'm drawing squares for my quads here, so I have a size variable, right? So if this is mx, my up here, mx, my, right? So this is the coordinate for the top left. Then my next vertex is going to be what? mx plus size my, right? Because I'm adding this size of my quad to get to the next vertex. Down here, this is going to be mx plus size, my plus size. That's how I get down here. Then over here, it's simply mx, my plus size. All right? So that should be pretty obvious why that is, and that's what we're going to go do now, is we're going to take these, and we're going to say exactly what we just did. So this is vertex 2 and vertex 3, and then here, vertex 1 was mx plus m size, right? Was that the variable name? Yeah, it certainly was. Next, we're going to have mx plus m size, and then my plus m size. And then down here, we have mx and my plus m size. So we've given each of our vertices their initial position, okay, which is the very center of the screen. Now, if you wanted to make this initial position somewhere else, that's fine. You would just change it up here, but this is what we're going with for now. All right. Next, actually, let's give it a color. So let's give it a color. So what I have to do for this now, so this is actually dot position. I forgot to add that because the position, that's the position. Now what we do is we're going to give each of those a color. So color equals, and now we have to give it a color. So I'm not going to be doing any gradients or anything. I want to give each of these vertices the same color, but I want that color to kind of be randomized, okay? So what I had last time was I had a random color between white and purple. So how would I create a random color between white and purple? So if we remember, purple is this, or this. So purple is when we have R, G, B, A, so red, green, blue, and alpha. This is red, so maximum red, maximum blue, that's purple. And we also have maximum alpha, right? So what I've done here, this is pure unfaded purple. Let's try and make like a randomized purple somehow. Okay, so I'm going to have, let's say int random alpha equals rand mod 255. So my random, I'm going to make my particles have a random transparency. Actually, let's not do that yet. I'll show you what this looks like first, and then we'll see why I might want to do what I'm explaining that I want to do. So this is going to be my color right here, which is just an all-out purple. And I'm just going to set this equal to color. And then I can do this for the rest of the vertices as well. Okay? So whenever I reset a particle, I'm giving it a color and I'm giving it a position. So that's what I've done so far. And down here in my draw system, I'm drawing those vertices. I'm not doing anything with the update yet, but let's just see what happens when I run this, if it runs at all. Okay, so all of my particles have been given the position of the center, and now I'm drawing 1,000 quads right on top of each other. That's what's happening. All right. So let's go on with the next step. Now that we've got, like, we know our vertex array is working, we're drawing quads, however, they just happen to all be on top of each other. So let's give this particle some sort of velocity. So let's say I want to give this a random velocity. So I'm going to have, how do I do this again? So float random x velocity is going to be, let's say, if we want a random floating point number, we're going to take rand and divide it by rand max, right? So this is going to be float rand divided by rand max. That is going to be a random number between 0 and 1, and maybe I want to multiply this by like 5 or 3, right? So I want to have a random velocity with some tangible value, and I'm going to do this in the y direction as well. So up here in my particle vector, each of them has this velocity. So I am going to say m particles, and this is index dot velocity equals SF vector 2F Rx Ry. So each of my particles is going to be given a velocity, and let me give the particles a lifespan. So, oops, apologies. My particles are going to be given a lifetime, equal to, let's say 10 at the very least, or let's just give them 100, all right? So, or 60. So each of my particles is going to last for 1 second. So now I run it again. What's going to happen differently? Nothing. Why isn't anything happening yet? Well, I gave them a velocity, but I didn't update the positions. Okay? So I didn't update the positions. So now I'm going to come to my update function. This update function is where we actually apply the physics to all of our particles. Okay? So for each of my particles, I've already gotten this loop done. I'm going to say, now here I have to update the positions of my particles, which is right here, right? So I can copy this like this. Now this is going to be I instead of index. And then what I have to do is I have to add something to that, right? So the position of each one, I'm going to say equals or plus equals, I hope it has m particles I dot velocity. All right. So each of the positions of each of those vertices, right? If I want to move it, well, let's say, for example, that this was my velocity v, right? This is my velocity right here, this vector. Well, in order to move the whole quad, I have to move each of these vertices by that amount, right? Because if I just move, for example, if I just move one vertex by that amount, then I won't be, this is the quad that I'll be drawing right here. So I have to be sure to move all of the vertices and not just one vertex, because it'll screw everything up. So let's do that. We're going to add the velocity of the particle to each of its vertices. Alrighty. So let's just run that. We haven't done anything with the lifespan yet, and we'll see what's happening. What have I done? This is kind of interesting now. Someone let me know what I did wrong here while I'm typing. The next thing that I'll do before I fix that is I'm going to deal with the lifespan. So before I update the positions, I'm going to say, okay, if particles I dot lifetime is equal to 0, so if if this is the life, like if the lifetime of my particle has expired, then what I'm going to do is I'm going to call reset particle. And that will be on index I. So what that does is, if my particle goes off for the full duration of its lifespan, I'm going to reset it. So instead of like killing it like we would do in ECS when its lifespan is up and like completely destroying it, right? We're just going to reuse this particle. So we're going to reuse it by just resetting its values. And so what this does is there are no dynamic allocations anywhere in this program. Nothing is ever truly being removed. Nothing is ever truly being added. We're just modifying this big contiguous data structure that we have. So if the lifespan has expired, reset the particle. Otherwise, we're going to say, take one away from the lifetime, right? All right, so now what we should see is they head out for 1 second and then they reset. Now, why are all of them doing this? It's because each of them have been given the same lifespan, right? So first of all, let's fix that lifespan problem. So let's go up and we'll add, okay, so the lifespan, I want them to be around for at least half a second and maybe up to rand mod 60. So what this means is we've got at least half a second, because it's 60 frames per second, and a random number between 0 and a second. So at least half a second, at most 1.5 seconds. Now let's rerun it again, now that they've been given a randomized lifespan, right? And now we've got that sort of effect that we're looking for of particles living and dying at sort of random times, right? Okay. Now, someone in the chat answered why I have this box-like structure, and it's because I have both of my values for velocity being positive. So let's take a screenshot of this, and I'll come over here. So here is what's happening. So let's crop this. If I were to make a graph, over here, of x and y, remember, y goes down in SFML, right? So down here is where I have positive x. So this is positive x and positive y. Up here would be positive x and negative y. This would be negative x and positive y. And this would be negative x. No, sorry, that's negative x and negative y. This is negative x and positive y. So essentially, I need to make sure that my velocities are randomized within the whole space of positive and negative integers, right? So let's go back up to my reset particle, and where I gave them this sort of random initial velocity, what I can do is something kind of clever, is if I wanted it to have a maximum velocity of 3, but now I want it to be between -3 and 3. What I can do is change this to, let's do 5 instead of 3. So here, if I want these to be able to be from -5 to 5, well, all I need to do is change this to 10. So now it has a spread of 10, and then I subtract 5 from it. And so what this will do is at the very least, this is going to be a 0. At the very most, it's going to be a 10. So if I subtract 5 from this, right, then it's going to be at least -5 and at most +5. So let's try it again. Here we go. Okay, so now we've got everything going out in this sort of this way that we've expected. But now you can see that, well, we can't really appreciate all the different particles because they're all exactly the same color, right? So let's give them sort of a randomized color. So at first, let's just give them a completely random color. So what I could do here is, well, I'm going to leave that there, but I'm going to say color equals SF color. Here I'm going to have rand mod 255, and I'm just going to do that for each of them. So it's going to be given a random red, green, blue, and alpha value. So it's going to be a completely random color for each particle. And that might look pretty cool, right? Actually, it does look kind of cool. It's pretty neat. However, what if I wanted them to all, maybe I wanted like a fire, right? So maybe I want them to be like all shades of red, right? So if I wanted them to be all shades of red, then what I could do is be like, okay, there's no green and there's no blue. So if there's no green and no blue, then it's going to be a random amount of red, right? So this is how you can tune the colors. So these are like a random color of red, right? And you might say, okay, that's pretty dark. So instead of it being so dark, let's say I want like at least like 55 here so that it just sort of brightens up everything a little bit. And so you can go through and you can like tailor your colors, but now I've got some grays in there. So maybe I actually want like 128 plus rand mod 128 for my red color. So now we should have like brighter, truer reds in here, right? So now maybe it's more of what you were looking for. Okay. But let me put something in here. I want to be able to reset my particles whenever I want. So I'm going to make this a public function. Okay. And I'm going to go in here and I'm going to say, if I press any key, oops. So if this is a key event, I'm going to say mParticles, particles it's called, .reset particles. Okay, so every time, keyboard, key pressed. Every time I press a key, it's going to reset the particles. Okay, so let's do this. Look at this. You notice how there's like an initial explosion whenever I reset the particles? That's not what I want. This is very common when you're first starting with particle systems. And that's because what we've done is we have spawned every single particle at the same time initially, right? That lifespan randomness doesn't really help for the very first spawning of all the particles. Now, if you want like an actual firework explosion, this is great, but we don't necessarily want that, right? So here's how I personally fix this problem. Now, there might be a more elegant solution, but what I do is the following. Whenever so in my reset particle function, what I want to do is say, if this is the first time that I've spawned this particle, so at the very beginning, I want it to be invisible until the first time its lifespan expires. Okay, so in here, I'm going to have a Boolean that I pass into reset particle, which is called first, and that's by default going to be false. Okay, so whenever I give it a color here, I'm going to say if first, then color.a equals 0. That's it. And so the first time it spawns, it's going to be given a completely transparent color. So it doesn't matter what the color is, this means it's invisible. And then only when I call this from the initial reset particles, I pass in true to that. And what that does is that the very first time everything spawns, it's invisible. And then after the first lifespan, see, it starts to slowly come in. So that's the way that I implement that. And there may be a more elegant way to do that, but that's so quick and dirty and it just works that's how I end up doing it. All right. So, I mean, that's a particle system. That's all you have to do to implement one. And you can think of so many different things that you can do with this now. All right. Let's do maybe, let's add What are we going to do? Let's just do one more thing. No, I was going to say let's make it so that when I click, it'll set the emitter position, right? But all year we've been dealing with like how to set a position. So what you may do in here, for example, is you could have an SF vector 2F, and this would be emitter. I guess that's how you say emitter. And so this emitter position, instead of using the window size.2 or window size.x divided by 2, window size.y divided by 2, you would say that the initial position is the emitter instead of this, right? And then if you have an emitter over here, like maybe I click the mouse here and now the emitter is over here. I click the mouse here, maybe the emitter is over here. If you, for example, wanted to have particles coming from different places at the same time, what you could do is maybe you have an array of different emitters, right? And then up here, you could say int emitter or emit index equals 0, for example. So what you could do then is maybe you have 3 different or 4 different or 1,000 different emitters in your level. Let's say, for example, you have a level with a bunch of different torches in it and you want sparks coming off of the torches. Here, you could have like torch index, right? So this is the index of the torch, which is the location of the torches down here. And then instead of mwindowsize.x, you would say, okay, well, you have the actual, so what would you do? You'd say float mx equals m particles dot torch, or m particles index dot torch index. That's the index of the torch. Then you would have the position of the torches indexed by this, and then that would have an x and a y. So this is how you would set up your mx so that the initial position of this particle was back at the torch that this should be spawning from, right? So you can have multiple emitter positions in your level as well. You don't just have to have a single position. And rather than like sit here and, code all that up and show you, just you can visualize that coming from different positions, right? Oops, this is I've just broken everything now. So let's just run it one more time. And the last thing I want to show you is, okay, we've got our particle system. You could have it exploding. You could have it doing this. I did a particle system for 4303. So if you're interested in game AI, let me show you this particle system. Now, this is probably going to hurt the bit rate, okay? So here's a particle system that I did for 4303. And essentially, this is a vector field assignment. And if I turn on particles, then random particles spawn at random places in the map, and then they use this vector field to actually pathfind to a particular location. So if I press the H button, toggle nav mesh display, toggle vector, okay, toggle nav mesh display. Okay, so now picture that I have a level. I can increase the number of particles, right? And as I move this around, you can see that the vector field is updating and this is doing all that like cool pathfinding stuff. So this is exactly how I made the vector field for this. Let me increase the number of grid cells. There we go. Okay. So I've got more grid cells now and the pathfinding is looking a little bit nicer. Yeah, so this is like a pathfinding vector field example where I have, let's see how many particles I can fit on the screen. Particle count, 16,000, 32,000, 65,000, 130,000 particles running at still over 100 frames per second. Okay, 100,000 particles, and this is using the exact same system. So rip bitrate, I know, I apologize. Let me make it a little bit smaller. Maybe that'll help. Okay, yeah, the video codec doesn't like 100,000 particles. But you can see how powerful this is and how easy it is to implement. Now, this particle system had, let me let me reset this. This particle system has far more advanced like physics because it's colliding with walls and stuff like that. But essentially, it's what we just did.